example of a linear equation. Anything that involves an x and a y, let's say, is a linear equation. And they're both raised to an exponent of 1. If the exponents on the x or y are anything other than 1, then it's not a linear equation. Okay, we call it a linear equation because if it is of this form, with x and y being raised only to the first exponent, then our graph is going to be a straight line. That's why we call it a linear equation. So just like we did in the previous section, if we're asked to solve this and graph it, generally we want it in terms of y. So we're going to solve this for y and say subtracting 2x from both sides, and now we have it in an easier form to graph like we had in 1.1. Now in 1.1 we were asked to graph these equations. In this section we're going to be asked to solve for one of the variables when we're given the other one. So in this section when we have a linear equation, we're just going to have one unknown and we're going to solve for that. So solving linear equations is what we want to accomplish here. So let's say we have 3x plus 7 equals 2x. Now here the only variable is x. We want to solve for x. So the idea here is to solve this equation for x. We want to know what x makes this equation true. So when we're solving for one variable, we want to gather all the terms that have that variable on one side of the equation, gather them together, and then isolate the variable we want. So we want to come down here and eventually get to a point where we just have x on one side and our answer on the other side. Right? So we got 3x here and 2x here. So if we subtract 2x from both sides, right, which we can do, remember to solve these we can add the same thing to both sides of the equation. We can subtract the same thing from both sides of the equation. We can multiply by anything other than 0, both sides of the equation, and we can divide by anything other than 0, both sides of the equation. It's a balance, right? We have to keep the balance. So if I take this 2x away from this side, I have to take 2x away from this side. So if I subtract 2x from both sides, I get 1x plus 7, and 2x minus 2x gives me 0 on the other side. So I subtracted 2x from the 3x, the 7 is untouched, and subtracted 2x from 2x. So now just to get to here, all I got is one more step, subtract 7 from both sides, and I end up with x equals negative 7. And I would like you to get into the habit of doing this, circling your answers, labeling them. It's just nice to organize your work. All right, so that's an example of solving a linear equation. Now you can always check this to make sure it's right by putting that x value back into the original equation and making sure that it's true. So if I put a negative 7 in here for x here, in here, I should get a true statement. So let's do that. 3 times negative 7 plus 7, does that equal, because we don't know yet, we're checking to see if it does equal. So we'll put a question mark there on the equal sign to see if it is. So remember our order of operations, again something very important, prerequisite, that's a very common mistake in this class, forgetting order of operations. You do multiplication before you do addition. So we're going to multiply this together first before we add this, and then we're going to multiply this side together also. So negative 21 plus 7, does that equal negative 14? And we see that it does, right? If we subtract 7 from both sides, we get a true statement, which shows us that we got the right answer. Okay? So that is solving a linear equation. And let's see. So let's look at an example with fractions, because I know we all love fractions. And I'm just getting these out of your book. You know, this is why you want to go through the suggested problems in the syllabus. These are all the types of things you're going to be expected to know how to do. So let's look at, let's say, number 22 on page 118. All right, so 22 on page 118, we have an example of a linear equation, x over 2. equaling 3x over 4 plus 5. Okay, this is still a linear equation. Notice the x is only raised to an exponent of 1. We're being asked the same question we were here. Solve this equation for that x. What x makes this true? So when we're dealing with fractions like this, what we want to remember is how to find the least common denominator. And these are things that we should know coming into the class. Prerequisites: a least common denominator is the smallest magnitude number that all the denominators divide into evenly. So here it's pretty easy. If we look, sometimes it's nice to make everything into a fraction when we're dealing with fractions. So if you want to make that a 5 over 1, sometimes that helps me just to make everything a fraction, keeps it a little more orderly. So we're looking at 2, 4, and 1. So the least common denominator here, the smallest number that all three of these numbers divide into evenly, is 4. So that is our least common denominator. So what we do is we multiply both sides of the equation by that least common denominator. We multiply both sides, and again, just looking at it as a fraction to make it easier to multiply. And now we're going to multiply both sides of the equation. Remember, we're not changing the equation. We're multiplying both sides by the same number. So the x values that solve this equation are the same values that are going to solve the new equation we're going to come up with here. So here the 4 over 2, this becomes 2. So we have 2 times x on the left-hand side. And here we're using our distributive property. We're multiplying this fraction by this fraction. So notice the 4 and the 4 cancel out. So we have 3x over 1, which leaves us with 3x. So notice what's happening after this step. We're getting rid of the fractions. Right? The fractions are going to disappear. And here, this fraction times this one, 4 times 5 gives us 20. So now we're back to very similar to what we saw over here. We're solving this linear equation, same idea. You can bring the x's to either side. If you want to bring the x's to the left-hand side, you're going to have a negative x. If you bring the x's over here, then we can bring the 20 to the other. So either way, just isolate the x. Let's subtract 3x from both sides here to get negative x equals 20. Right? So I subtracted 3x from 2x. Subtracted 3x from 3x on this side to be left with the 20. Now we're not solving for negative x, we're solving for positive x. So we multiply both sides by negative 1 and we get our answer, which again I'll leave the check to you so we can get through these quickly. But again, if you want to check, just put this back in here and here and make sure you get a true statement. All right, so that is a linear equation with fractions. So another step up in difficulty here in this section is when we have variables in the denominator. So we want to deal with that. Let's look at an example like that. So I'm going to look at number 36 on page 119. And this is an example of a linear equation, but the difference, notice, is we have variables in denominators which we haven't dealt with before. So that is the added layer of difficulty here. Sure I wrote that right. All right, so the procedure is the same. Right? We're going to do exactly the same procedure that we did over here, but now we have this x to worry about. So here there were no x's in the denominator over here, so we knew our answer, as long as we did our calculations right and it checked out, was going to be a valid answer. But sometimes, not necessarily in this example, but sometimes when you're dealing with these types of equations, you'll end up with an answer that we can't allow. Like if we got an answer of 0 for here, if we work this out and get an answer of 0, we can't accept that answer because it makes this denominator equal to 0 and it makes this denominator equal to 0. So that's the added step here. We have to make sure our answers are valid answers. Sometimes we're going to get more than one answer. Sometimes when we try to solve these, we're going to end up with a quadratic, which we haven't really talked about yet, but we'll get more than one answer. Sometimes one will be valid and one won't. That's why it's important to check your answers. So you can either do that before or after. Like in this case, it's pretty easy to see the only answer we can't accept is 0. All right, so we know if we come up with a 0, we cross that out and we say that's not a valid solution. So we're going to do the same thing we did over here. We're going to look at these denominators, 2x, 9, 18, and 3x, and come up with a least common denominator. So if this confuses you when you have numbers and letters together, think about it separately. Just like we looked at just the numbers over here, just look at the numbers first, the 2, the 9, the 18, the 3, and determine what is the smallest number that all 4 of those numbers divide into. I think the easiest way to do that is to just look at the largest number and ask yourself if that's the least common denominator. 2 goes into 18 evenly, 9 goes into 18 evenly, 3 goes into 18 evenly, so that is our least common denominator. If that wasn't, then you go to 36. Then you'd go to 54. Just take multiples of the largest number until you get the smallest one that they all divide into. In this case, 18 is the least common denominator. Now for the variables, you take the variable the maximum number of times that it appears in any one of the denominators. Okay, the maximum number of times that it appears in any one of the denominators. So x appears once here, 0 times here, 0 times here, and once here. So 1 is the maximum number of times that it appears in any one of the denominators. So that's the number of times that it's going to appear in the least common denominator. So that's our least common denominator. And now we're back to where we were in the previous example. We're going to multiply both sides of the equation by that least common denominator. I'm going to put it over 1, again, just to make it clearer as to what's going on. And again, now we got distributive property on both sides. So we multiply this fraction times this fraction. And you can multiply it out and then simplify. I think it's easier if you can see the simplification first. It just makes the numbers smaller. So you look at the 18 over 2, and you see that's going to be 9. And the x's are going to cancel out. So the 18 over 2 is 9. 9 times 5 gives us 45. Right? The 18 over 2 became 9. 9 times 5. The x's canceled out, so there's no x's left there. This fraction times this fraction, we got a minus, so it's minus. And remember, after this step, the reason we're doing this is because it'll make the fractions disappear, and then we'll just be left with a linear equation with no fractions. So this fraction times this one, again, simplify, 18 over 9 becomes 2. So I got 2 times x times negative 8, so that's negative 16x. I did that right. 18 over 9 is 2, 2x times negative 8 to get the negative 16x. And similarly, over here, this fraction times this fraction, the 18's cancel out, so I'm just left with the 1 times x. And this fraction times this fraction, the x's cancel out, 18 over 3 becomes 6, so I'm left with x minus 6. And now again we're back to hopefully familiar territory, linear equation, no fractions, gather the x's together, solve for x. So let's add 16x to both sides here. So we'll leave the 45, add 16x to this, no more x's on the left-hand side. Adding 16x to 1x gives me 17x, and I still have the minus 6. I want to isolate the term with the x in it, so I'm going to add 6 to both sides. 45 plus 6 gives me 51. And when you get a nice even multiple like this, makes you think you did something right. You divide both sides by 17 here, and 51 over 17 is a nice even 3. And remember, we have to make sure our answer makes sense. We already determined that the only answer we cannot accept was 0. This is not 0. 3 is our only answer. Again, I'll leave the check for you. Put the 3 back in, and you should get a true statement. All right, so that is linear equation with fractions and with variables in the denominator. All right, so last thing in this section is just identifying. Sometimes you'll be asked to identifying equations. There's three things that can happen when we try to solve an equation. We can either get an answer like we did here and like we did here. We got an answer. We got at least one answer. So I'll set this up as an if-then. All right. So if we get at least one solution, then we call that a conditional equation. Conditional. Think about it, it's true conditioned. This equation is true conditioned on the fact that x is negative 20. Right? This equation is true conditioned on the fact that x equals 3. So it's either conditional. Sometimes we're going to get no solution. Sometimes we just can't get a solution. So I'll give you a quick example of that. Let's say we're talking about this equation, and we want to try to solve this equation. So we go through the methods we just discussed. We distribute this 2, we get 2x minus 6, it's 2x plus 7, but then we try to gather the x's. If we subtract 2x from both sides here, we get a false statement. Okay, so that's your clue that there's no solution. If you try to solve the equation, the variable is eliminated, and you get a false statement, that's going to be the case where there's no solution. Okay? And we call that inconsistent. So sometimes you're going to be asked to classify an equation or identify the equation. Classifying or identifying an equation, you're going to be asked to identify it as conditional, inconsistent, and the last choice is, what is the last choice? Identity. Now an identity means, so this is an example of no solution. And here would be an identity, would be something like this. If you're asked to solve this equation, just like we tried to solve this one, we distribute the 2, and we see we get the same thing on both sides. If we eliminate the x's, subtract 2x from both sides, we end up with a true statement. So notice the difference here. When we tried to solve this, we ended up with a false statement. That tells you there's no solution and it's inconsistent. When you try to do that, solve the equation, the variables are eliminated, and you end up with a true statement. That means it's an identity, and any x makes this true. I can put any value of x in here, and it ends up with a true statement. That's what an identity is. So this is an infinite number of solutions. And those are the three things you want to be aware of. You want to be able to solve any equation. We did the 3 different types: a linear equation with no fractions, a linear equation with fractions,